All right, good morning. That was sad. Let's do that again. Good morning. Much better. So today we're going to look at 15.8. We're still doing triple integrals. We'll be doing triple integrals for a little while. And we'll be looking at triple integrals in different coordinate systems. Today we'll be looking at what's called the cylindrical coordinates. And each of these coordinate systems we look at is advantageous for certain shapes, certain situations. And we'll be looking at all of these details as we go over these things. First of all, cylindrical coordinate system. We have actually seen this before. We just never really gave it a name. In cylindrical coordinates, a point is represented by three numbers, r, theta, and z. And essentially what cylindrical coordinate system is you have a polar in two of these. So what's really going on here is you have polar in the xy plane. So you get your r and theta. And it is a rectangular coordinate system in z. So think of it as a hybrid system here. In the plane, xy plane, it's polar system. But the height of that is given the usual Cartesian z. Hybrid system. So a point in three-dimensional space. And as usual, r and theta is always measured from the positive x-axis. Just like polar. And r, of course, is the distance in the plane from the origin. So this is r. And z is just how high that point is. So now we located the shadow of that point in the xy plane. Now we go up z amounts. So the point really sits right here. R, theta, z. Okay? Polar in the xy plane, and then just a typical Cartesian height in the z direction. The conversion, we already know that. You know how to convert from polar to Cartesian. So going from rectangular to cylindrical, it's just the usual polar conversion for x and y. R squared is equal to x squared plus y squared, right? That's the Pythagorean identity. Tangent of theta is equal to y over x. That's how we find theta. And lastly, z doesn't change. Z is equal to z. So whatever z is in the original Cartesian system, it carries over into the cylindrical coordinate system. Going backwards from r theta z to xyz, from cylindrical to Cartesian, it's again the conversion you already know from polar back to Cartesian. So the very familiar expressions, x is r cosine theta, y is r sine theta, and of course z doesn't change. Z is still z. Okay, so we've seen this before already. It's polar plus one additional rectangular system. Nothing really new about it. All right, so let's do a quick example of a conversion here. In Cartesian, the point is minus 3, 3 radical 3, and 1. And let's find out what it looks like in the cylindrical system. Okay, so all we know, you just have to remember that z doesn't change. Z is still z. That stays the same. And then we got two things remaining, x and y. They are essentially polar. So in the xy plane, x is minus 3 here, and then y is 3 radical 3 here. And above this picture here, we have a height of 1. So the point really is up here, but the point casts a shadow onto the xy plane right here. And we only care about the shadow of that point, because that's where r and theta are defined. As usual, remember that theta is defined from the positive x-axis. And then r, of course, is the distance from the origin on the x and y plane. Right? So r is easy to find. R squared is x squared plus y squared. So that's equal to 9 plus 27, 36. Therefore, r is equal to 6. And we always take the positive r, even though we could allow that to be negative, but customarily we take that to be positive and let theta be whatever angle that results from that. Theta comes from tangent of theta is equal to y over x. So here we get 3 radical 3 over negative 3. So negative radical 3. And when you do this thing here, we're going to be taking an inverse tangent next. You got to be careful with your quadrants. If you don't sketch the picture, then this equation here alone gives you two possible answers. You have negative tangent, so it's either in the second or the fourth quadrant. But if you have the picture here from the point, then it's very clear which one you're going to go into. So use the picture to help you to decide which one it is. In this case here, it's a quadrant 2 angle that we're looking for. Okay, so be very careful that when you do an inverse tangent, you're going to get two answers. And there's only one right answer. They can't both be right. For us, we're looking for a second quadrant angle. So theta turns out to be 2 pi over 3. It's negative 3, radical 3 over 2 over 1/2. So it's 2 pi over 3. So therefore, in the cylindrical system, our point minus 3, 3 radical 3, 1 is going to be 6, 2 pi over 3, and z is still 1. Okay, once again, you leave the z alone, and then you do a polar conversion in x and y. Stuff you already know how to do. Questions? All right. Let's look at some of the surfaces describing a cylindrical system. Suppose we have a surface z is equal to 4 minus r squared. And let's try to find out what this thing looks like. All right, look at this here. When r squared is equal to 4, z is equal to 0. So what this is telling you is that whatever this thing is going to look like a circle of radius 2 on the x and y plane. Right? When z is equal to 0, we have r squared is equal to 4, so therefore a circle radius 2 on the x and y plane. And the maximum z is equal to 4. Z never gets above 4, right? When r squared is equal to 0. So that means there's a point at x equal to 0, y is equal to 0, and z is equal to 4. That's the tip of the surface here, and z has no chance to get ever above 4. And lastly, looking at z here, z can get, well, let's start sketching what we got here. You can probably recognize what this is just by noticing these things. All right, 0, 0, 4, that's right here. And on the x and y plane, we see a circle of radius 2. And notice that as z gets below x and y plane, when z is negative, that means r squared keeps on getting bigger and bigger. So we get bigger and bigger. The circle gets bigger and bigger as z gets lower and lower. All right, so what is this surface that we're staring at here? Cross sections are circles. And opens down. What's this? Paraboloid. Yep. This is our paraboloid that opens down like that. Now, if you had trouble identifying that, one thing you could do is to always go back to Cartesian. R squared is x squared plus y squared. So this is 4 minus x squared minus y squared, right? So if you're used to seeing these things in Cartesian and you're presented with a polar equation or cylindrical equation, change it back to Cartesian. See if it helps. Now, if you had trouble identifying them in Cartesian, then obviously that's not going to help. But you could still come up with the surface just by looking at cross sections. The stuff that you know about surfaces, traces and all that is still valid. Choose a z to be a constant, and was looking at circles. do another one kind of like that. Let's sketch the region really a solid described by this set of conditions. Theta is between minus pi over 2 and pi over 2. And r is between 0 and 2. And z is between 0 and r squared. Okay? It often helps if you start by looking at the xy plane. Just look at these two conditions here. Worry about z after we're done with that. So looking at the x and y plane, that's going to give you what it looks like on the xy plane, or the shadow of this object on the xy plane. Theta is between minus pi over 2 and pi over 2. Where is negative pi over 2? The negative y-axis, right? Right? Remember, theta is always measured from the positive x-axis. So right here is theta equal to 0. Theta is negative pi over 2, means it's over here, into the fourth quadrant on the x and y plane. Okay? So on the x and y plane, we're going to be looking at a half circle with a radius of 2. So 2 here, negative 2. All right? Now let's look at the z equation. So obviously, z is between 0 and r squared, means z is always between 0 and r squared. Z is greater than 0, so this is above the x and y plane. Easy. Now we're going to figure out what this shape is. If we can figure out what z is equal to r squared looks like, then we know the region we want is always bounded below this thing and above the xy plane. So what is z equal to r squared? Look at the last example. It'll help you. What do we have? Paraboloid opens which way? Up, down, left, right. Up, yeah, positive z, right? It has a radius of 0 at z equal to 0, and the radius grows with z. So, yeah, this is a paraboloid. Paraboloid opening up. All right, so this is what we got. So we want everything that's above this half circle but below the paraboloid. Above the half circle on xy plane and below the paraboloid. So what we end up getting here, this is if you take a cylinder and then you squeeze a paraboloid in there, remove the paraboloid, and then chop the cylinder in half. That's what we got here. It's a half. I'll sketch it from a slightly different perspective. Okay, so it's a cylinder with the paraboloid taken out and then chopped in half. And we want everything that's below that, so we hollow that out. We just take this thing here. That's what we want. Questions about this? Good? Okay, let's move on. Cylindrical is good for, as the name implies, anytime you're dealing with a cylinder-like thing. So, of course, cylinders are good. And very often, paraboloids are also very, very good. Kind of solid to go into cylindrical coordinate system. Sphere is not as good. We'll be looking at a different coordinate system for spheres next time, but for now, just remember cylindrical is good for cylinders and any paraboloid-like object. So for example, suppose we started with a Cartesian triple integral. So right now we're in Cartesian. And you look at this thing here, you know you're going to get a very, very nasty integral if you start by integrating in Cartesian. The first one is easy. The first round will be very, very easy to do because there's no z in here. So you just simply gain a z, and this gets multiplied by that. Starting with the second round, then you're going to get into a big, big problem. You're integrating square root of x squared plus y squared times 9 minus x squared minus y squared with respect to y. That's a nasty integral to deal with in Cartesian. So when that happens, perhaps it's a good thing to try to go into cylindrical. And also notice right here, this is a paraboloid. Okay? And this thing right here, that's a circle. Circle is part of a cylinder. So we're dealing with a circular region of some sort with a paraboloid bounding above, below, or something like that. These are indications that it's a good idea to at least try going to cylindrical before you brute force through the Cartesian. In fact, it may not even be doable if you stay in Cartesian. All right, so let's check out what's going on here. Looking at this here, we see that x, simple bounded, is between -3 and 3. And y is bounded between 0 and radical 9 minus x squared. And remember, going to cylindrical means we don't do much with z. Z stays put. We just have to translate this from Cartesian to cylindrical before we integrate. So we're going to be operating with x and y to find r and theta. -3, +3, and what's this? What's square root of 9 minus x squared? It's a semicircle, right? Half a circle, upper half or lower half? Upper half, right? 0 to that, so it's got to be the upper half. What's the radius? 3. All right, so this is the region we're dealing with. And then above this region, there's some kind of z going on. That's fine. We don't have to worry too much about that z. We're not changing too much with z. All we need to do from here is to get out r and theta bounds. Okay? So, how shall we bound theta? How should we bound r? Zero to pi, good, and r 0 to 3. We want everything inside the half circle. 0 to pi, 0 to 3. Z, we don't have to operate much at all. Z is between 0 and whatever it was originally given. We just have to change this from Cartesian to cylindrical, and then we'll be okay. So we got to go to cylindrical first. X squared plus y squared is equal to r squared, so that's 9 minus r squared. Right, so when I use this one, okay, so that difficult integral in Cartesian is going to turn into something pretty simple. It's going to go from 0 to pi for theta, and then 0 to 3 for r, and then 0 to 9 minus r squared for z. And what's this in cylindrical? R, right? R. What's dz, dy, dx in cylindrical? dz doesn't change. Z has not changed, right? So we need a dz somewhere, of course. And z is going to start. What about dx and dy? What do they become? RD theta, very good. Don't forget that R. Because in polar, dx dy is equal to r d theta, or dy dx, doesn't matter. Right, so we get an r here, but out of these three d stuff, we get an extra r. And then we have dz first, dr next, d theta last. All right, so you look at this integral here. This is pretty easy. We can actually integrate that very quickly. Whereas the Cartesian one, we would have a lot of trouble. dz, dr, d theta. Yep. All right, so we get 0 pi, 0, 3. No z here. The first round of integration gives me an extra z, and z is really that. So this becomes r squared times 9 minus r squared dr d theta. And both of these are easy. Yeah. Right, but square root of r squared is r, right? So we gain another r. So in the end, we get r squared, but we do have an extra r coming from the dv. Zero pi, 0, 3, 9 r squared minus r to the fourth, dr d theta. This is easy. 0 pi, 3r cubed minus 1 over 5r to the fifth, 0, 3 d theta, 0 pi 81 minus 3 to the fifth, whatever that is, 243. 243. Is that right? You can calculate that. All right, there's no theta in here, so I just gain an extra pi. And at the end of this, we should get 162 pi over 5. Okay, so cylindrical, relatively easy, actually very easy, whereas in Cartesian, very, very difficult. Okay, so on the exam, if we throw an integral at you and it's in Cartesian, don't just jump in and start integrating and get stuck. Look at the regions you're dealing with. If you see a cylinder or a paraboloid or anything cylinder-like, anything dealing with a circle of some sort, chances are paraboloid will be a very good, cylindrical will be a very good coordinate system to work in. If the region is a rectangle, of course you want to stick with a rectangular. Okay, let's do another example. Let's find the volume of the solid bounded below by z is equal to 0, bounded laterally on the sides by x squared plus y minus 1. Quantity squared is equal to 1. And above by z is equal to x squared plus y squared. All right, so again, first of all, noticing this stuff we're dealing with. This is a circle of some sort. This is a paraboloid of some sort. These two together tells you that cylindrical is good. Okay, this is a situation that you do not want to stay in Cartesian, because chances are it'll end up being a big mess. Whereas in polar, it may be a little bit difficult to set up, but the integration will be easier to do. All right, so now suppose we made a decision to go to cylindrical because we've seen a circle, we've seen a paraboloid. Now we're going to translate these equations into polar and cylindrical, and then we move on from there. Let's start with that circle. Let's change that to cylindrical, which for x and y together, that's equivalent to polar. Right? Cylindrical is polar in x and y in two of these, and then Cartesian in something else. Okay. What is x in polar? Well, let's multiply this out first. So this is x squared plus y squared minus 2y plus 1 equal to 1. All right? So what's x in polar? R cosine, right? So r squared. Well, actually, what's x squared plus y squared in polar? R squared, yeah. What's y in polar? R sine. Plus 1 minus 1, those go, plus 1 and 1, those go away. So we have a 0 here. So this is equivalent to r is equal to 2 sine theta. And what is this? This is a circle of radius 1 centered at 0, 1. So it's a circle that's offset from the origin. Okay, so what do we got? We got this thing right here, circle centered at 0, 1, right here, radius 1. And we want everything, so this is a cylinder coming out of the page. Imagine a circular cylinder coming straight out of the page. What we want is something that's bounded by that cylinder and a paraboloid above it. A portion of that cylinder that's below a certain paraboloid. Can you visualize that? Yes? Okay. So it's bounded above by that. So let me try to sketch that. Okay, in this view here, we have our cylinder. Goes up. So this goes up infinitely, initially. And then above this, we have a paraboloid. Z is equal to R squared. We want everything that's inside this cylinder, but everything that's below that paraboloid. And what we end up wanting is this thing right here. I'm going to try to sketch this. Try being the key word. What do you think? Good? I say that's pretty good. What do you think? So, can you visualize what we're dealing with? We want the volume of this thing right here. This, I don't know what you would call it. It's a portion of a cylinder with part of it taken out. Some kind of ramp, whatever. Whatever you call it, that's what we're trying to find the volume of. Okay? Again, this is the kind of thing that you do not want to attempt in Cartesian. Cylinder and circle and paraboloid. Cartesian is going to be a nightmare. Okay, let's set up the bounds in cylindrical. Look at the region on the xy plane again. Theta is always the simple set of bounds to set up. And in this case, what would my theta bounds be? What do you think? We want everything in this circle, right? So in polar, what we're doing here, we're accumulating all of these little green stuff. We want to accumulate all of these green lines as it sweeps from one end to another. So we start our accumulation toward the x-axis, and we end our accumulation toward the negative x-axis. So my bounds would be what? 0 to pi, right? What about r? R is how far you go with these green lines. Where do you start? Where do you end? Where do we start? 0. Yep. Where do we end? 2 sine, right. Remember, this circle R is 2 sine theta. Right? That's the circle that was offset. So that would be the upper bound of R. Just remember that in polar, you're basically sweeping that green line all the way through and accumulating all of that as it sweeps around. So look how long each of these green lines will be, starting at 0, ending at whatever line that is, whatever curve that is. And theta is always the simple one to set up. Where do you start? Where do you end? What about my z bounds? What's bounding below? 0. What's bounding above? Right, the paraboloid. Yep. We're hitting the lower surface of the paraboloid, so that's r squared. Okay, now the volume of that funny-looking cylinder would be 0 to pi, 0 to 2 sine theta, 0 to r squared. And what do we integrate to get a volume? What do you integrate to get a volume? Integrate 1 times dV. Yep. So what's dV? Say it again. Very good. So you integrate 1 to get your volume, yes. And dV is dz r dr d theta. Right? This is the volume, the dV, being cylindrical. And this is just your usual dA in polar. Stuff you already know. And you integrate 1 to get your volume. All right, first round of integration is with respect to z. We have an r. When you integrate r is a constant right now, you gain a z. So rz is the first round, 0 to, z is equal to 0, z is equal to r squared, and dr d theta after that. Rest of this is pretty straightforward. And then here we get r cubed, right? Dr d theta. Next round, we get 0 to pi, 1/4 r to the 4th. And r is going to go from 0 to 2 sine theta, d theta. So we end up getting 0 to pi, 1/4, 2 sine theta to the 4th power. 2 to the 4th is 16 sine 4th d theta. How do you integrate sine to the 4th? We did that last time. Something very similar last time. Remember the identity to use? No? Yeah. 1 minus cosine 2 theta over 2. Right? So that's the identity we want to use for that. Okay, we'll finish that up. That shouldn't take very long. So, 0 to, what is it? Pi, yep. And then we have 4, 16/4, I'll take that outside. Inside here, we got this thing squared. So it's 1 minus cosine 2 theta over 2 squared d theta. There's a 1/4 and the 4 out there. Those cancel. So 0 to 1, 0 to pi, 1 minus 2 cosine 2 theta plus cosine squared 2 theta d theta. That's easy. That's easy. What about this? What do you do with this? The cosine version of that identity, right? Okay, so 0 to pi, 1 minus 2 cosine 2 theta. That's going to be plus 1/2 plus 1/2 cosine of what? What's twice of 2 theta? Well, 4 theta, right? It's twice of this. 4 theta. Okay, rest of this is easy. You should end up getting, what is it? 3 pi. Huh. It's amazing that volume of that strange looking thing turns out to be such a nice number, 3 pi. Okay, if you're shaky with doing stuff in polar, you better sharpen your skills with that, because when we go to the next coordinate system, all of these are going to be all messed up in there. So if you're shaky with polar, make sure you do something about that. All right, see you next time. Because when you do inverse tangent, you will get what's called the principal value. That's always the smaller. Okay, that makes sense. Yeah. Actually, inverse tangent.